Okay, so thank you for waiting. It's my great pleasure to introduce the second speaker this morning, Professor BrunoKahn from Institut de Mathématiques de Jussieu, Paris, also CNRS. So he will tell us on the injectivity and non-injectivity of the l-adic cycle class maps. So please start.
Thank you very much, and also thank you for inviting me to this conference. It's always a pleasure to be back to Komaba. So, I will, yes. So, it's kind of a sequel of the previous talk. Claire introduced algebraic cycles over an algebraic variety, so I'm going to repeat a little bit what she said. So here we are over a field, a general field K, and we can take the free abelian group with basis the closed integral subvarieties of a given algebraic variety. So obviously this is an important invariant of the algebraic variety, but it's too coarse, because with this you cannot, for instance, you cannot do intersection theory. For instance, if you take a smooth projective surface and you take two curves, so if they are generally, you can intersect them and you can count the number of points. And if they are not in completely general position, then you can define multiplicities of these points and then make sense of an intersection number. But what happens if the two curves are equal? And you want something. So the solution is you have your two curves which are equal and you move one of them. And then you hope that when you have moved it, of course, it becomes different. And you want to take their intersection number as the self-intersection of the curve. And if this kind of process respects the intersection number, then you win, and this is the case. And to move, it's a bit like in homotopy theory. It's moving along, let's say, affine lines. So I'm not going to give details on this, but once this is done, you get a quotient of Zn of x that you call Chow n of x, and it's the nth Chow group of x. And if x is non-singular, so I'm going to say smooth for non-singular from now on, then you can also number by codimension, and you get codimensional Chow groups, Chow upper n of x. So for instance, for n equals 1, Chow 1 of x is the Picard group of x. As Claire said, it describes isomorphism classes of line bundles over x. Okay. So then one wants to understand these algebraic cycles, and to do that, one compares them with cohomology, and that's cycle class maps. So the most classical case is when you are over C. This is what Claire said in her talk. She talked about cycle maps, so a class, a cohomology class associated to an algebraic cycle. And here I'm saying a little more, which is that this map factors through rational equivalence, which is true. But here I'm going to work over any field. So instead of singular cohomology or Betti cohomology, I'm going to use étale cohomology. So, yes. So we take a prime number which is different from the characteristic of K. And then in SJ 4.5, there's a cycle class which is constructed, which goes from the Chow groups of X modulo a power over L to some étale cohomology group. And then, the one question which is usually asked about these cycle class maps is surjectivity of them over some subgroup of this kind of group. So here, this is the Hodge conjecture, and over finitely generated field, this would be the Tate conjecture for l-adic cohomology. So to make sense of the Tate conjecture, you cannot work with finite coefficients, and you take stronger coefficients. So you take the projective limit of these of these groups, and then you get a cycle class with values in this group, and then there's a Galois action, and the Tate conjecture says that tensor Q should be surjective on the Galois invariance. So if you are over a general field, you could take this definition, but it's not very nice because it's not, for instance, the functoriality is not very good. So Janssen defined the right object, which is, he called it continuous étale cohomology. So I'm not going to give the definition, but this is the group which is not good. This is the one which is right, and then it sits in a Milnor exact sequence. So there's a lim1 on the left. So it means, and then Janssen constructs an l-adic cycle class map with value in this continuous étale cohomology, where I have forgotten the twist. Zn, it's even worse. Sorry. But it goes from this group to that group. So it's even richer because there is this gadget. And then, so here is the first result. We want to understand this cycle class map. So our first result is that the image, so if you are over a finitely generated field, the image of the cycle class map is finitely generated ZL module. And this is essentially due to Shuji Saito in an article of 1992, I guess. Then, after understanding the image, one would like to understand the kernel. And that's the subject of the talk. So, one question is, when is the cycle class map injective? So if it's injective, we are very happy because we completely detect cycles modulo rational equivalence. But it's a bit too much to ask over a general field, because if you're over an algebraically closed field, well, already for a smooth projective curve and for n equals 1, it's completely false because Chow1 of X sits between the Néron-Sévry group, which is finitely generated, and pic 0 of X, which is the points of the Jacobian of X over K. And this is a divisible group, and therefore the whole of pic 0 of X is killed by the l-adic cycle class map. But if K is finitely generated, Janssen proved that this map is injective. So it depends heavily on the nature of the base field. And I'm always going to talk about finitely generated fields. So finitely generated means finitely generated over its prime subfield. So in characteristic 0, it means finitely generated over Q. And in characteristic P, it means finitely generated over FP. So in some sense, you can understand the philosophy that it's injective, because in this case, one knows that Px is a finitely generated abelian group. So there is some morality that it's injective. And in general, well, there's a conjecture on Chow groups. I'm not going to talk about it. I'll just mention it. It's called the Bloch-Beidelssohn-Murray conjecture, which says that if X is smooth projective, there should be an interesting filtration on Chow n of X tensor Q. And Janssen proves that if the cycle class map tensor Q is injective, then this Bloch-Beilinson-Murray conjecture is true. So it's a quite important question. If you look at the literature, you see that people study the injectivity of this cycle class map, but only respected to the torsion of the Chow group. There are some positive results in the same paper of Shuji. And then some counterexamples, which are much more recent. So I know 3 papers, one by Scavia and Suzuki, one by Alexandru and Schreier, and one by Koliotelen and Scavia. And for me, it was a bit strange because you look at the question modulo torsion, but they don't try to study what happens tensor Q, which would be the first thing to look at, I think. And then, first thing I wondered is the converse to Janssen's theorem that the injectivity tensor Q implies BBM. Does BBM imply the injectivity? And the answer is I don't know. I tried to prove it and failed. For me, if you want to have an idea whether a question is reasonable or not, I'm going to look for a known conjecture which would imply this result. So that's what I tried to do. And then, so that's this third question here. Are there some conjectures which are known which would imply the injectivity tensor Q? And the answer is yes in positive characteristic, but in characteristic 0, I don't know any such conjecture. So I'm going to explain that. Now, let me take a smooth projective variety over a finite field. Then there's the Tate-Beilinson conjecture, which is that this cycle class map tensor Q is bijective for all n greater than or equal to 0. The surjectivity is the Tate conjecture, and the injectivity is basically the Beilinson conjecture. And then the result is that this conjecture implies that the cycle class map tensor Q is injective, but not only over Fp, but over any finitely generated field over Fp, so in positive characteristic. And the proof is not very simple, not very hard, but it's easy to explain. The main point is to get out of smooth projective varieties and to enlarge the statement to all smooth varieties over Fq, over Fp. And then now you take a finitely generated field over Fq, like this one. Then you can write it as the function field of some smooth variety. And you can spread X to a smooth projective morphism to U, provided U is small enough. And then one nice property of continuous étale cohomology, I talked of functoriality, is that you have Loret spectral sequences. Then you look at the Loret spectral sequence corresponding to this morphism, and this is a smooth projective morphism, so there's a degeneration criterion of the linear for this Loret spectral sequence, which involves using how do you say like it's hard Lefschetz basically. So you take a smooth hyperplane section, and then you take cup products with this, and if you are clever enough, you see that it degenerates the spectral sequence. And then basically that it's sufficient to see this. And sorry?
So the conjecture one, you need the bijectivity.
Bijectivity over FQ and over FP, and that's bijectivity. It helps to pass from smooth projective to smooth. Here, this X is smooth.
Injectivity in conjecture one is not enough. You actually need bijectivity.
No, it's not. So now I'm going to talk about these things, studying the cycle class map restricted to the torsion. So first thing is some positive results. So decomposition of the diagonal means I have a smooth projective variety, and I assume that the degree map from 0 cycles of X over its function field to Q, that this map is an isomorphism. And then I'm only going to look at Chow2. So morally, when you have such a degenerate situation, it drops the complexity by 1, which means Chow n of X behaves like Chow n minus 1 of some other smooth projective variety. But it's very rough. It's, let's say, it's tensor Q. So there's a chance for such a variety to be able to get some positive results for Chow2. And that's what the theorem says. So it says that now here it's tensor Q, but let me drop tensor Q. Then there's really a degree. So it's this integer delta. So first thing, delta kills the kernel of the cycle class map. Yes. Mm-hmm. And then, so this kernel is torsion in particular, and it's finite if K has Kronecker dimension at most 2. Kronecker dimension, so it's in characteristic P, it means it's the transcendence degree over Fp, and in characteristic 0, it's the transcendence degree over Q plus 1. It's a kind of arithmetic dimension of the field. And this was in characteristic 0, and in characteristic P, it's a bit annoying because you have to say it's the same thing, but up to some P primary groups. And then, well, all of it is due to Shuji Saito, still in the same paper, but except he does it when delta is 1, he shows that it's injective, and over number fields. So the add-on in this theorem is the case of Kronecker dimension 2. So it means function fields of surfaces in characteristic P and function field of a curve over Q in characteristic 0. And in both cases, the point is to use that Chow 0 of arithmetic surfaces is finitely generated, which is due to block in characteristic 0 and Saito in positive characteristic. So what happens is, I said there's a chance that you can be successful, but when you look at the proof, what happens in detail, you see that, in fact, the size of the base field shows up, and then you need to know something on the Chow groups of its model. So this limits it to curves, and the proof is not so easy to do. So that's all for positive results. And then the negative results. So the counterexamples. Well, I want to separate them in two types. First, for Chow 2, and then for Chow n with n bigger than 2. And the way I wanted to understand these examples is to remember that this cycle class map can be factored through something which is called étale-Chow groups. So étale-Chow groups are defined as étale motivic cohomology. I'm not going to give definition. It's not as elementary as ordinary Chow groups. And then for n equals 2, the relationship between Chow2 and Chow2 et al. Is given by a short exact sequence like this. So in particular, A alpha 2x is always injective. But when n is bigger than 2, it's not injective in general. And then when I look at these counter examples, I thought for n bigger than 2, maybe they are already killed by alpha n. And it's true. So theorem is that in all examples, the cycle which is killed by the cycle class map is already killed by this map alpha n x, which is here. And this makes all proofs basically trivial. It's much easier to work with étale motivic cohomology than with l-adic cohomology. So, for example, Alexandru and Schreier introduce what they call refined block maps, and they are not necessary because this vanishing has nothing to do with continuous étale cohomology. It's just a matter of étale-Chow groups. Then there's another, so for n equals 2, there are basically two examples. So in Scavia and Suzuki, they look at an example which is inspired by the proof of the Bloch-Kato conjecture. In this proof, you take a norm variety, and it has an associated Rost motive. So for p equals 2, a norm variety is of the form, you take, if you know what is a Pfister form, so this is a form of dimension, a quadratic form of dimension 2 to the n minus 1, and then you add this, so it's 2 to the n minus 1 plus 1, and then you take the smooth projective hypersurface with this equation. This is a norm variety. And then for p odd, they are much more difficult to construct, and there is a so-called Rost motive, which is in the category of Chow motive, which is the direct summand of the motive of such a norm variety. And then it's well known that its second Chow group is Z mod L. So here we fix a prime number L. And then one way to understand their counter, so they show that this element vanishes in l-adic cohomology. The cycle class map of this is 0 when the base field is well chosen. And what happens is that first, if you take étale-Chow groups, then étale-Chow groups don't see this Rost motive. Here I have localized at L. This is not ZL, it's Z localized at L. And the Rost motive lives in Chow motives with these coefficients, so I don't need to put it here. But in any case, it's this Chow2 et al. Reduces to the one of the base field. And then the second map in my decomposition is 0 because the target is 0. This is the target, and it's 0 because k is chosen to have cohomological dimension 3. So that's the way to explain their counter example. And then there's the one of Colutelen and Scavia, and this one I needed a lot more work to work out what's going on, and it's not completely clarified because there are some maps in their work and some maps that I cook up, and one would have to show that they are equal, and it doesn't seem so straightforward. And that's all.